Okay, now in this one, recall that Fn is the vector space of all n tuples or n vectors where the components are field elements. We have to prove that there is an isomorphism of Fn into this space. It looks somewhat complicated, but you can see what it is. It's the space of all homomorphisms from this space into F, and this itself is the space of all homomorphisms of Fn into F. So let us see how we can achieve this isomorphism. For any vector v in Fn, we define a function Tv from this into F by this formula. Now, what is the meaning of this function? Our Tv is our function and F is coming from here. So this F itself is a function from Fn into F. And in fact, it's not just any function, it's a homomorphism, a vector space homomorphism. So it makes sense to apply F on this vector V, or in other words, it makes sense to evaluate F at V, because V is a vector in Fn and the image of V under F is Vf. Note that because of the nature of this function which maps Fn into F, this Vf is an element of F, that is, it's a scalar. So for a given F here, we are actually getting a scalar, that means an element here under the function Tv. Fine. And one more thing that we need for well-definedness of Tv is that this image is unique. It is unique, of course, because for a given F, V anyway is fixed. So once we fix F, Vf is unique. And uniqueness of Vf for a given V and F follows from the fact that F itself is a well-defined function. Okay, so all of these things we are simply going to mention in one sentence, which is this. Clearly, Tv is well defined. Okay. Now the next thing we want to do with Tv, we want to show that Tv is a homomorphism, because after all it's a map between two vector spaces. So for that we will need a number of things. We will need a scalar, we will need two vectors from the domain space, and do we need anything else? No, just a scalar and two vectors from the domain space. So let F and G be two vectors here and alpha be a scalar. Then what happens when we apply Tv to F plus G? By the definition of Tv, this is the image of V under F plus G. Now this plus is the addition that we have in this space, and by the definition of F plus G, this is nothing but Vf plus Vg, and this is FTV plus GTV. This tells us that TV respects addition, and what is this? This is V alpha F, and in this space alpha F is the product of the vector F and the scalar alpha. So by the definition of this function, this is alpha times F image of V, which is nothing but alpha times V, oh sorry, this is not V, this is F. So TV also respects multiplication by scalars, hence TV is a homomorphism, i.e. TV is a homomorphism from this vector space into this vector space. That means TV is an element here. Okay. Now using this TV, we can now define a map between this space and Fn. We now define a map omega. There is no need to write omega or anything. You can write anything you want actually. Fn into I mean the name of the map, you can call it anything. By this formula, V omega is defined to be equal to TV. Since we have proved that for any V in Fn, TV is in this set, so this map makes sense, and also for a given V there is only one TV, so no problem with the uniqueness of TV. Clearly omega is well defined. You should understand that we will only write clearly something is well defined only when it is clear and it's not very complicated or indirect or cannot be seen at once. Okay, so now next we want to show that omega itself is a homomorphism, and in fact it's an isomorphism. So this is the isomorphism that we are seeking in this question. Okay, so for that so that means we will need two vectors in our original space Fn, a scalar in the field, and do we need two elements from this space? Two elements or one? I think one element is enough. Okay, so let u and v be two vectors in Fn, f be a vector in this space, and alpha be a scalar. Okay, then what is the effect of tu plus v on f? By the definition of tu plus v, this is the image of u plus v under f. Now since f is a homomorphism with domain Fn and u and v are vectors in Fn, so f respects addition, so this is uf plus vf. Okay, now uf is ftu and vf is ftv. Now by the definition of addition in this space, this is equal to ftu plus tv. This plus is the plus that we have in this space, addition. And note that now this is true, I mean these two functions give us the same value at the same vector f, which implies, so from that we have u plus v omega equal to tu plus v, and tu plus v is the same as tu plus tv, because they give us the same image of a given f, and this is u omega plus v omega. So omega itself respects addition. Also, f t alpha u is equal to alpha u f. Now f is a homomorphism and alpha is a scalar, u is a vector in Fn. So f itself respects multiplication by scalars. So this is equal to alpha times uf, or alpha times ftu. Now by the definition of multiplication by scalars in this large space, this thing is equal to f alpha tu, which implies that alpha u omega is equal to t alpha u is equal to alpha tu. So omega, besides respecting addition, it also respects multiplication by scalars. Thus omega is a homomorphism. Next, the next thing we want to show is that omega is 1 to 1. So if we can show that the kernel of omega consists of only the 0 vector, that will imply that omega is 1 to 1. So next, let A equal to Okay, now the kernel of omega we know is going to be a subspace of Fn. So that means if we are taking any element from the kernel, it's going to be an n-tuple in Fn. Belonging to Fn be any element in the kernel of omega. Okay, then A omega is the zero vector where? Zero vector in this complicated space. But we know what A omega is. TA is the zero homomorphism. Now we know that TA is a function from this space into F, and it's the zero function. That means TA maps every element in this space onto the field element 0 scalar for each integer I lying between 1 and n. We are going to define a map Fi from Fn into F by this formula. From Fn into F, so that means we are going to apply Fi on an n vector or an n-tuple of field elements. And our definition is this. This is equal to Bi. Okay. Now, our next claim is that each such Fi is going to be a homomorphism for any two vectors Ideally, we should have taken, because these are field elements, we should have taken Greek letters, but it does not change anything. And that is because in the beginning itself we have said that capital Latin letters will denote vector spaces, small Latin letters will denote vectors in the spaces, and small Greek letters will denote field elements, scalars. So if you want to stick to that, you can write beta 1, beta 2, etc. So these are any two vectors in Fn, and say alpha is any scalar. We have what happens when we apply Fi to the sum. We know that this sum is, inside Fi, the sum in the argument will be this. b2 plus c2 bn plus cn fi. Now this, by the definition of fi, is bi plus ci. Now bi itself is the fi image of the first vector and ci is the fi image of the second vector. So fi respects addition, and just like that, alpha times this fi alpha bi. Okay, this shows that fi is a homomorphism from fn into f for all integers I varying from 1 to n. Now the condition that we have here, we are now going to apply that condition to these fi's, because Ta is supposed to be the zero homomorphism on this space. So in particular, if we apply Ta to these fi's, we should get 0, namely the zero scalar actually. Thus FITA, but FITA, we have a definition for Ta, we know what the function Ta is. So this is AFI, but what is A? A is this. So this is equal to AI, and this is true for all values of I. So that means all the components of the vector A are 0. Hence, A itself is the 0 vector. Thus, the kernel of omega consists of only the 0 vector. So omega is 1 to 1, and hence is an isomorphism. Okay, so this completes the solution. Next, if U and W are are subspaces of a vector space V prove that U plus W, which is defined to be the set of those vectors that are sums of vectors in the subspaces U and W. This itself is a subspace of V. It's very easy. You can apply that criterion for a non-empty subset in a vector to be a subspace. Either you can do that or you can do something else also. Let us first go the easy way, the way we know. Since we don't even have to write since, clearly this is non-empty, because U and W are non-empty subsets of V, being subspaces themselves. So by the definition of this sum, it's also non-empty. So let us take two elements in U plus W, where U1 and U2 are coming from U and W1 and W2 are coming from W. Also, let alpha be any scalar, where F is of course the underlying field. We haven't, the exercise does not mention the field, but there is an underlying field. If you want, you can write F is the underlying field of scalars. Okay, then first of all, if we add these two vectors, then using the fact that our original vector space V is an abelian group under addition, and so addition is associative as well as commutative, we can rearrange the terms of this sum like this. Now, because U1 and U2 are in U and capital U is a subspace, so their sum is in U, just like that W1 plus W2 is in capital W. So this this sum belongs to U plus W. And w1 plus w2 belongs to w. Okay, so that means the sum of our two chosen vectors from u plus w is again in u plus w. Also, alpha times u1 plus w1 is equal to alpha u1 plus alpha w1, where to carry out this step we have used one of the vector space axioms in V, and this belongs to u plus w since alpha u1 belongs to u and alpha w1 belongs to w, again using the fact that u and w are subspaces. Thus, it's better to refer to the result that we will be using here. I mean that criterion which tells us when a non-empty subset of a vector space is a subspace, but I can't remember the exact number, or even whether it's a lemma or it was theorem, I don't remember, but you understand. So you insert that here. Thus by that lemma it follows that u plus w is a subspace of V. Now one can solve this using another technique also. Look at this u plus w. The elements in u plus w look like this. Because that's what the definition says. Now we know that our original vector space is an abelian group under addition, and being subspaces u and w are subgroups of V under addition, and this u plus w is actually nothing but the product uw in that subgroup. Because if we treat these as subgroups, then this u plus w is uw, recall that thing, kh. When k and h are two subgroups of a group, then we define the product of k and h. And we in fact proved in group theory that kh itself is a subgroup if and only if kh is equal to hk. Now since this is always true if we are in an abelian group, so in an abelian group the product of any two subgroups is again a subgroup. Now this is one such product. Because our operation is plus, so we have plus here. Okay, so u plus w is automatically an additive subgroup of V. So once you understand that, then the only thing you need to show is that u plus w is closed under multiplication by scalar. That is the second part. Namely, you take one element u plus w here and you take one scalar and show that their product is again in u plus w. So if you want that, we can write an alternate solution like this. The alternate solution goes like this. Since u and w are subgroups of V under addition, the result is lemma 251. Implies that U plus W is also a subgroup of phi under addition. So to prove that U plus W is a subspace, what are the things that are left? One thing is that you have to show that U plus W is closed under multiplication by scalar, and additionally those 4 axioms that come at the end of the definition of a vector space. But if you look carefully, those 4 axioms, since they are true in V, in particular they are also true in any subset, namely in our case U plus W. So it's enough to just show that U plus W is closed under multiplication by scalars. We have this calculation here, but just for the sake of completeness we write it once more. Where U belongs to U and W belongs to W, and also let alpha be a field element where F is the underlying field, that I am not writing again. Then alpha times U plus W is alpha U plus alpha W, which again belongs to U plus W. Since alpha U belongs to U and alpha W belongs to W, that's why so this is an alternate solution which looks somewhat shorter than this one, because the additive group part that is taken care of by lemma 251. Don't forget that part of a vector space is an abelian group, that is, under its addition any vector space is an abelian group. So whenever you deal with vector spaces, as far as group theoretic results are concerned, all of them are going to be true. And what more is true, the group structure in a vector space is an abelian group, so things are particularly nice. Then exercise 12. Prove that the intersection of two subspaces of V is a subspace of V. Just like this one, this also can be done in two different ways. One, of course, is just using that criterion for subspace, and the other is like this, using first showing that the intersection is a subgroup and then showing that it's closed under multiplication. multiplication by scalars. So which one shall we do? Let us use the subgroup criterion itself. But before that, we have to assume the two subspaces. Let U and W be two subspaces of V. Okay. Then U intersection W is non-empty. We are not even going to mention why it's non-empty, because you already know that the 0 vector belongs to both of them. So that's why it belongs to the intersection, and that's why it's non-empty. Always, before showing that a system is a subgroup of some group, or a subring of some ring, or a subspace of a vector space, make sure that the set is non-empty. Okay. Now let V1 and V2 be two elements in the intersection and alpha be a scalar, where f is the underlying field, not writing that again. Then V1 plus V2 belongs to U, alpha V1 belongs to U, comma V1 plus V2 belongs to W, and alpha V1 belongs to W. This is because U and W individually are subspaces. So these vectors will belong to them. This implies V1 plus V2 belongs to the intersection of U and W, and alpha V1 also belongs to the intersection. Hence, this is a subspace of V. Okay, I urge you to try the alternate solution also, where first of all you have to argue that this intersection is a subgroup of V under addition, which will come from results in group theory, and then you show that this intersection is closed under multiplication by scalar, which is just this. So this is the solution. Okay, then exercise 13. If A and B are subspaces of V, prove that A plus B by B is isomorphic to A slash A intersection B. Now we have come across this type of thing in group theory in one of the exercises, where in place of a vector space we had a group G and we had normal subgroups N and H. I don't remember exactly if both N and H were normal, but normality of course is there. And then we had to prove that NH by N is isomorphic to N by N intersection H. Since this result, whatever the case is, I mean, you can see that in our case the subgroups are normal because our additive group in the vector space is an abelian group, so every subgroup is normal. So since this result is available to us, we are going to use it, and we write the solution like this. The solution to exercise 6 of section 2.7 shows that A plus B by B is, or we can also write like this: this is isomorphic to A by A intersection B as groups. Okay, and in fact the map F, which maps A into A plus B divided by B, and which is defined like this: AF is equal to A plus B. I think this is the map. Do I have the map here? Yes. Turns out to be an onto group homomorphism with kernel A intersection B. So because this map is a group homomorphism, that means it respects addition, because that is our binary operation with respect to which our original space V is an abelian group. So the only thing we have to now show extra to complete the solution is that F respects multiplication by scalar, because you see F already respects addition. Now if F also respects multiplication by scalar, then F will be a vector space homomorphism from the subspace A to this quotient space A plus B by B. And as far as kernel is concerned, the kernel of this group homomorphism is the same as the kernel of the vector space homomorphism. You go back to the definition of kernel of a group homomorphism and a vector space homomorphism, you see that the definition of the kernel of a vector space homomorphism is based on the additive group structure. So kernel does not change, it's still the kernel. I mean, here the kernel is A intersection B, there also the kernel is going to be A intersection B, which is nothing but the inverse image of the 0 element here under the map F. So it's enough to prove that F respects multiplication by scalars. For any A belonging to A, and alpha belonging to F, we have alpha AF. By definition, this is alpha A plus B, this coset, which by the definition of multiplication by scalar in this quotient space is alpha times A plus B, and this is nothing but alpha times AF. So that's it, that's what we wanted to show. And this now automatically implies that F is a vector space homomorphism from A into this space whose kernel is A by B. So by the vector space isomorphism theorems, A by this is isomorphic to that as vector spaces. So we end the solution here itself. Then exercise 14. If T is a homomorphism of U onto V, where you should understand that U and V are vector spaces over the same field of scalars with kernel W, prove that there is a one-to-one correspondence between the subspaces of V and the subspaces of U containing W. Now we have already come across results like this in group theory as well as in ring theory. They are known as correspondence theorems. In group theory, the situation is like this. You have two groups, G and H, and there is a group homomorphism phi from G to H, G on to H, where the kernel is K. Then there is a one-to-one correspondence between the subgroups of H and the subgroups of G containing K, and in this correspondence normal subgroups correspond to normal subgroups. The version of this in ring theory is this. Say R and R prime are two rings, and F is a ring homomorphism of R onto R prime with kernel I. Then there is a one-to-one correspondence between the ideals of R prime and the ideals of R containing I. We have already proved this one, and in case of rings we said that one can similarly prove the things. Now the same thing we are going to say in case of vector spaces. Here we had subgroups, in ring theory we had ideals, here we have subspace. Same thing actually, you just proceed like how you proceeded in case of groups and group homomorphism, you will get the result. And in fact, the one-to-one correspondence we are talking about here is nothing but this. On this side you have V, on this side you have U. You take a subspace, say V prime of V, and you look at this, the inverse image of V prime under T, that will be some set here. Prove that this is a subgroup of, subspace of U that contains this kernel W, and then proceed accordingly like how you proceeded in case of groups and group homomorphism. So instead of again going through all those things, we are just going to write a hint of a solution, and we are going to call that hint itself the solution. Follow the discussion. Before lemma 275. So this is in group theory. You proceed accordingly, you will get the thing. Okay, then exercise 15. Let V be a vector space again. You notice that thing which we were talking about, we mentioned once before, three types of correspondence theorems: for groups, for rings, and for vector spaces. What is the reason for their similarity, and what is the reason they, things like this keep on appearing? You will understand those things when you go to category theory. Okay, so in the next exercise, let V be a vector space over F, and these are subspaces of V. suppose that V is the sum of these subspaces, where sum is defined, we have already defined it before for two subspaces U plus W. Like that, we can naturally extend this to any finite number of subspaces. So the author says, see exercise 11. And these conditions are also true. The intersection of Vi and the sum of the remaining subspaces is trivial. It consists only of the zero vector for every I varying from 1 to n. Prove that V is the internal direct sum of these subspaces. The solution is very easy actually. Since it's given that V is the sum of these subspaces, so every element in V is expressible in this form, where Vi belongs to Vi. To prove that the sum is a direct sum, you have to show that this expression, this sum expressing V as a sum of vectors of the Vi's is unique. To prove this uniqueness, you consider two such representations. Assume that they are equal and then use these conditions to show that actually the two expressions are identical. That is, if besides this expression you also assume V to be expressible in this form, where each Vi prime belongs to Vi, you will then have to show that V1 is equal to V1 prime, V2 is equal to V2 prime. That is, the two expressions are identical. For that, it's not very difficult. From this equality, you can see that you have something like this. Equal to V2 prime minus V2, V3 prime minus V3. Now look at this equation. In this equation, the left hand side, since it's a difference of two vectors in V1, so this belongs to V1, but the right hand side, this belongs to V1 and this belongs to, from the look of it, you can see that it belongs to this, but they are equal, so they will both belong to V1 as well as this. But according to the given conditions, this intersection consists of zero vector only, so both of these vectors must be equal to 0. From that you get the thing that V1 is equal to V1 prime. If you repeat this with 2 in place of 1 and then 3, 4 etc. all the way up to n, you can clearly see that these two sums must be identical. So that's how you write the solution. Now the thing is that instead of this is what the solution is, but even before getting this, one gets a corresponding thing in group theory. We have not reached to that stage. It comes in section 13 of the second chapter, which has group theory. So we are just simply going to write in place of a solution this thing. It follows from, in fact, not just it can be solved this way, but it actually follows from exercise 9 of section 2 13th section of the second chapter, to which when we arrive we will see how exactly it follows from that. There, in place of vector spaces we have groups, and in place of sums we have products, internal direct product, external direct product of normal subgroups. We have those things. Then exercise 16, let, if you are not happy with this, then you can in fact write the solution the way we have seen here. The hint that we have seen here of this solution, you can write that systematically, showing that the two expressions are identical and hence the sum is a direct sum. Next, let V be the external direct sum of these vector spaces. So here V1, V2 up to Vn, these are some given vector spaces over some common field F, and their external direct sum has been considered, that is V. Prove that in V there are subspaces. Vi bar isomorphic to Vi. Such that V is the internal direct sum of the Vi bars. This is also very easy. Instead of taking arbitrary, and let us take n equal to 3 and see what the solution is. So suppose V is this. V1 plus V2 plus V3. So that means as a set, V is the set of all ordered triples such that v1 belongs to v1, v2 belongs to v2, and v3 belongs to v3. And we know from the definition of external direct sum that the operations on this set, that is addition and multiplication by scalar, they are defined component wise, and in a single component the operations are those of the corresponding spaces. Okay, now this exercise says that in V there are vectors, subspaces that are isomorphic to these individual vector spaces, which you can clearly see is this. The V1 bar that they are talking about is nothing but this. It's extremely easy to see that V1 bar is isomorphic to V1. Then V2 bar is this. This is isomorphic to V2, and V3 bar is this. And I don't think it will be a very difficult problem to show that V is first of all the sum of V1 bar, V2 bar, V3 bar, because you can write this vector as a sum of three vectors, one looking like this. That is, those three vectors are actually this: V1, 0, 0, 0, V2, 0, and 0, 0, V3. And then you show that this expression of the original vector as a sum of three vectors from here is unique, much like how we were discussing there. So that will prove that V is the internal direct sum of the Vi bars. Now here also, just like this hint, one can come from group theory, and in group we haven't got to that stage, but when we do, we will see that all these things already have group theoretic versions. Ideally we should go like this. Now we complete group theory, and then we complete ring theory, and then only we start vector spaces. So in place of a solution, if you want, you can write a solution like this. In place of 3, you just will have n, and things will follow accordingly. Now in place of an actual solution, here also we are going to, you can say, cut corners. See the discussion in section 213 that appears before the definition of internal direct product. Same, whatever you see here, there also you will get the same thing, but for groups, and the notation is also same. Here we are considering Vi bar, there you will see Ni bar, where Ni are normal subgroups. Okay, there are other exercises also in this set of exercises, so in the next video we will complete them, and then we will move to the more interesting parts of vector space theory, namely the part which has the notions of linear dependence, independence, basis, dimension, those things. Okay, so you please do these things that we have discussed here today. I mean, some of them are, especially this one and this one, they are incomplete. So you try to complete them the way we have discussed. So that will be all for today. So until the next video, this is, oh, I forgot one more thing. You may be thinking that I silently abandoned number theory and graph theory. The reason is that I have been busy in the weekends for, in something. So that thing is over, that thing has been completed. So this weekend we are again going to start from where we left, number theory and graph theory. So with that, this is me, Lucifer, from A Mathematical Room. Have a nice night.